3i Atlas is heading straight for Jupiter. Not close to Jupiter, not past Jupiter. Directly into the exact boundary where Jupiter's gravity takes over from the Sun. 53.4 million kilometres. That number matches Jupiter's Hill sphere to within 60,000 kilometres. The odds of a random trajectory hitting that precise target? 1 in 26,000. And here is what keeps me up at night. 3i Atlas will reach that boundary on March 16th, 2026. The same boundary where objects can be captured. The same boundary where satellites require almost zero fuel to stay in place. The same boundary you would aim for if you wanted to leave something behind. What 3i Atlas does when it gets there, that is the question nobody at NASA wants to answer. Like and subscribe if you truly love these topics, and let us begin. The mathematics of orbital mechanics are unforgiving. When an object enters our solar system on a hyperbolic trajectory, meaning it is not gravitationally bound to our Sun, and will eventually leave again, its path is dictated by the laws of physics with almost perfect predictability. We can calculate where it will be months or even years into the future based on its velocity, its angle of approach, and the gravitational influences it encounters along the way. This is not guesswork. This is the same mathematical precision that allows us to land rovers on Mars within meters of our target zones. So when NASA's Jet Propulsion Laboratory, using data from over 230 observatories around the world, calculated the future trajectory of 3i Atlas, they arrived at a number that made some astronomers do a double take. On March 16th, 2026, this interstellar object will reach its closest distance to Jupiter at precisely 53.445 million kilometres, with an uncertainty of only plus or minus 60,000 kilometres. Now here is where this gets fascinating. Jupiter has what scientists call a Hill radius. Think of it as an invisible sphere surrounding the planet where Jupiter's gravity dominates over the Sun's gravitational pull. Inside this sphere, Jupiter is king. Objects can be captured, can orbit, can become permanent residents of the Jovian system. Outside this sphere, the Sun's gravity wins, and objects simply pass by. The Hill radius of Jupiter on March 16th, 2026 will be exactly 53.502 million kilometres. Do you see what happened there? The predicted closest approach of 3i Atlas differs from Jupiter's Hill radius by less than 60,000 kilometres. That is a margin of roughly 0.1%. In astronomical terms, that is not close. That is identical. That is threading a cosmic needle with a precision that defies statistical explanation. Professor Avi Loeb of Harvard University was among the first to highlight this extraordinary coincidence. In his analysis, he calculated the probability of a random interstellar object achieving this level of precision. His conclusion was striking. The odds work out to approximately 1 in 26,000. But that number assumes we're dealing with a completely random trajectory, an object that happened to drift through our solar system purely by gravitational chance. What if we are not? Consider for a moment what the Hill radius actually represents for a hypothetical visitor to our solar system. The boundary of the Hill sphere is where Jupiter's Lagrange points L1 and L2 are located. These are positions of gravitational equilibrium where objects can remain stable with minimal fuel expenditure. If you wanted to place satellites or monitoring devices around Jupiter, these would be the optimal locations. The fuel requirements for station keeping would be minimal. The vantage point would be commanding, and anything deployed there would remain in Jupiter's sphere of influence indefinitely. This is not idle speculation. This is precisely how we design our own space missions. The James Webb Space Telescope sits at Earth's L2 point for exactly these reasons. We understand the strategic value of Lagrange points because we exploit them ourselves. Now 3i Atlas is approaching not Earth's Lagrange points, but Jupiter's, and it will arrive at the precise distance where those points exist. Think about that for a moment. The skeptical mind, and I count myself among the skeptics until evidence compels otherwise, immediately asks whether this could simply be coincidence. After all, the universe is vast. Improbable things happen all the time. Given enough random events, even unlikely outcomes become inevitable. But here is where the mathematics become uncomfortable. This trajectory precision is not the only anomaly 3i Atlas has displayed. It is merely the latest in a growing list of statistical improbabilities that, when multiplied together, produce odds that strain the boundaries of coincidence. The probability that 3I Atlas would arrive from a direction aligned within 9 degrees of the famous WOW signal from 1977 is roughly 1 in 170. The probability that its retrograde trajectory would align within 5 degrees of the ecliptic plane of our planets is about 1 in 500. The probability that it would pass within tens of millions of kilometres of Mars, Venus and Jupiter, while remaining hidden from Earth, based telescopes at its most active period near perihelion, is roughly 1 in 20,000. Each of these probabilities taken alone is unlikely but not impossible. Combined, the product of independent probabilities gives us numbers that venture into territory where coincidence begins to feel like a less satisfying explanation. And yet we must be careful here. The human mind is notoriously poor at intuiting probability. We see patterns where none exist. We assign meaning to random clusters of data. This is why science demands rigour, demands replication, demands multiple lines of evidence before entertaining extraordinary conclusions. So what does the evidence actually tell us? 3I Atlas displayed what scientists call non-gravitational acceleration during its passage around the Sun. This is not unusual for comets. As ices sublimate and gases jet from the surface, they can push the object slightly off its purely gravitational path. Think of it as a natural rocket effect. The question is whether the observed acceleration is consistent with natural outgassing, or whether it represents something else entirely. NASA's Jet Propulsion Laboratory recorded a non-gravitational acceleration of approximately 5 times 10 to the negative 7th astronomical units per day squared during perihelion. This is small but measurable, and crucially, this small acceleration is precisely what was needed to adjust the trajectory of 3I Atlas from a path that would have missed Jupiter's Hill radius to one that will arrive exactly at its boundary. Let me say that again because it is important. The measured non-gravitational acceleration, occurring while the object was hidden behind the Sun and unobservable from Earth, produced exactly the course correction needed to achieve the Hill radius match. Not more, not less. Exactly right. Professor Loeb frames this as the 13th anomaly in his catalogue of mysteries surrounding 3I Atlas, and he poses a question that mainstream science has been reluctant to engage with directly. If this object were technological in origin, if it were designed to deliver something to Jupiter's sphere of influence, this is exactly the trajectory you would design. The counter-argument is straightforward. Natural comets do experience non-gravitational forces. We have observed this phenomenon countless times. The specific magnitude and direction of that force for 3I Atlas could simply be a cosmic roll of the dice that happened to produce this remarkable alignment. Improbable does not mean impossible. Furthermore, we must consider observational bias. We notice the anomalies precisely because they are anomalous. We do not write papers about the countless interstellar objects that presumably pass through our solar system without displaying any unusual characteristics. Perhaps 3I Atlas is simply the statistical outlier in a much larger population of utterly mundane interstellar visitors. These are valid points. They deserve serious consideration, and yet they do not fully resolve the central mystery, because here is what we do know with certainty. 3I Atlas is heading directly into Jupiter's gravitational sphere of influence with a precision that is difficult to attribute to chance. It made a course correction at the optimal time, while hidden from our view, of exactly the magnitude required to achieve this precision. And it did so while displaying a suite of other anomalies including unusual jet structures, bizarre chemical abundances, and brightness variations that have puzzled observers since July. The Juno spacecraft currently orbiting Jupiter will have a front-row seat when 3I Atlas makes its closest approach in March 2026. In fact, a team of researchers, including Professor Loeb, proposed earlier this year that Juno could potentially be redirected to intercept 3I Atlas, getting close-up observations that no Earth-based telescope could match. That proposal would have required a manoeuvre in September of 2025, a window that has now passed. But Juno's instruments will still be watching from their orbit around Jupiter, able to detect whether anything unusual accompanies 3I Atlas as it grazes the boundary of the Hill sphere. What might they find? Perhaps nothing more than a natural comet, remarkable only for its interstellar origin and its improbable trajectory. Perhaps evidence of fragmentation or unusual outgassing that explains the trajectory anomalies through purely natural mechanisms. Or perhaps, just perhaps, something that forces us to reconsider our assumptions about what wanders between the stars. The data we collect over the coming months will be crucial. December 19th marks the closest approach of 3i Atlas to Earth, a distance of about 270 million kilometres. This will be our best opportunity to study the object with ground-based telescopes and space observatories before it continues its journey toward Jupiter. High-resolution spectroscopy could reveal whether the jets we've observed are consistent with natural sublimation, or whether they display characteristics more suggestive of directed thrust. Careful tracking could refine the trajectory predictions and either confirm or complicate the Hill radius coincidence. And then we wait for March. We wait to see whether 3i Atlas simply passes by the boundary of Jupiter's domain, continuing on its journey out of our solar system forever, or whether something else happens at that gravitational threshold. Something we cannot yet predict. But the Hill radius is only part of this story, because the trajectory that brings 3i Atlas to Jupiter's doorstep is itself the product of a journey that likely began billions of years ago in a stellar system we cannot identify, under circumstances we can only imagine. And the object making that journey has displayed behaviours since its discovery that challenge our understanding of what an interstellar comet should look like. The jets emanating from 3i Atlas in recent weeks have been captured by amateur astronomers with a clarity that has surprised even professional observers. These images reveal structures extending millions of kilometres into space, collimated beams of material that should have been smeared by the object's rotation, but instead maintain their precise orientation across exposure times that should blur them beyond recognition. The jets that refuse to blur. On November 9th, 2025, two amateur astronomers named Frank Niebling and Michael Buchner pointed their telescopes at a faint smudge in the constellation Virgo. What they captured over the next 15 minutes would add another layer of mystery to an already perplexing cosmic visitor. Their composite image, stacked from 5 separate 3-minute exposures, revealed something that by all conventional understanding should not exist. Two needle-thin jets extending toward the Sun, accompanied by a longer collimated stream stretching nearly 3 million kilometres in the opposite direction. And here is what made veteran observers pause. These jets were sharp. Impossibly sharp. 3i Atlas rotates. We have known this since July and August, when careful photometric analysis revealed a rotation period of approximately 16.16 hours. This is not unusual. Most comets and asteroids rotate. But rotation creates a problem for long exposure imaging of jets. As the nucleus spins, any gas or dust being ejected should trace out a spiral pattern, a corkscrew of material that smears across the image as the object turns. Over a 15-minute exposure, with a 16-hour rotation period, we should see noticeable spreading of any jet features. We do not. The jets from 3i Atlas maintain their tight collimation across exposure times that should absolutely blur them into diffuse fans. They extend to distances of over 1 million kilometres, while remaining as straight and focused as a laser beam. This is not what natural cometary outgassing looks like, or at least it is not what any comet we have ever observed looks like. Professor Loeb catalogued this as the 12th anomaly in his growing list of mysteries. His analysis is straightforward. If material is being ejected from the surface of a rotating nucleus at the thermal speeds expected from sublimating ice, roughly 400 meters per second, then that material should take about a month to traverse 1 million kilometers. During that month, the nucleus completes approximately 45 full rotations. The jet should be wound into an elaborate helix, a spiral structure that spreads the material across a wide angular range. Instead, we see needles. There are potential natural explanations. Perhaps the jets are not continuous streams, but rather discrete puffs that were all ejected at similar times, creating an illusion of collimation. Perhaps the rotation axis is aligned in a way that minimizes the apparent spreading from our viewing angle. Perhaps the material is being ejected at speeds far higher than thermal velocities, reducing the time it takes to traverse the observed distances and thus reducing the rotational smearing. Each of these explanations has problems. The discrete puff hypothesis struggles to explain why multiple observations on different dates show the same collimated structure. If we were seeing momentary ejections, the appearance should change dramatically from day to day as old puffs disperse and new ones form. Instead, the jet morphology has remained remarkably consistent across weeks of observation. The viewing angle explanation requires a rather specific orientation of the rotation axis, one that just happens to align in a way that minimizes smearing for Earth-based observers. This is possible, but adds another improbability to an already improbable object. The high-velocity explanation is intriguing but raises its own questions. Natural cometary outgassing is driven by solar heating of volatile ices. The temperatures involved produce gas molecules moving at hundreds of meters per second, not thousands. To achieve the kind of collimation we observe would require ejection velocities many times higher than thermal processes can explain. What mechanism could produce such velocities? One answer, and I want to be clear that this remains speculative, is technological propulsion. Rocket engines and ion thrusters produce exhaust at velocities far exceeding anything natural sublimation could achieve. A spacecraft using directed thrust would produce exactly the kind of collimated jets we observe, jets that maintain their structure because they are propelled at speeds that minimize the effects of rotation. This is not the only interpretation, but it is an interpretation that the data does not exclude. The images captured by amateur astronomers in mid-November revealed something else that has generated considerable discussion. 3i Atlas displays what astronomers call an anti-tail, a jet of material extending toward the Sun rather than away from it. Now, anti-tails are not unheard of in cometary science. Under certain geometric conditions, when Earth passes through the plane of a comet's orbit, dust left behind in the comet's path can appear to project sunward due to perspective effects. This is well understood and well documented. But the anti-tail of 3i Atlas is different. When the high-rise camera aboard NASA's Mars Reconnaissance Orbiter captured images of 3i Atlas during its close approach to Mars in early October, it confirmed something important. The sunward extension was not a perspective illusion. It was a genuine physical structure, material actually extending in front of the object along its direction of motion. This was observed from Mars, from a completely different vantage point than Earth, eliminating the geometric explanations that would apply to a perspective-based anti-tail. What kind of comet produces a genuine forward-facing jet continuously, for months on end? The conventional answer would invoke unusual nucleus geometry, or localized active regions that happen to point toward the Sun due to the object's orientation. And this is certainly possible, but it requires yet another specific configuration, another unlikely arrangement that just happens to produce behavior we have never documented in thousands of observed comets. Professor Loeb has suggested an alternative interpretation. For a technological object, a forward-facing emission could serve a practical purpose. Interstellar space is not empty. It contains dust, gas, and occasional larger particles that would pose a hazard to any object travelling at the velocities 3i Atlas has achieved. A forward-facing beam, whether of particles or directed energy, could serve as a debris shield, vaporizing or deflecting material before it impacts the main structure. This is precisely how we would design a long-duration interstellar probe. We would need some mechanism to protect it from the accumulated damage of billions of years of travel through the sparse but not empty void between stars. Again, this interpretation is speculative. It cannot be proven with the data we currently have, but it is consistent with the observations in a way that challenges us to think beyond conventional assumptions. The jet activity observed in November 2025 was significantly more complex than anything seen earlier in 3i Atlas's passage through our solar system. Images from November 8th, captured by a team of European observers, revealed at least 7 distinct jets emanating from the nucleus in various directions. Some pointed toward the Sun, some away, some at oblique angles. The overall structure resembled nothing so much as a spacecraft firing multiple thrusters simultaneously. Of course, natural explanations exist here as well. An irregular nucleus with multiple active regions, each containing different volatile ices sublimating at different rates depending on solar illumination, could theoretically produce such a complex jet structure. We have seen hints of similar complexity in other comets, though never quite to this degree. The mass loss implied by this activity is substantial. Professor Loeb's calculations, based on the observed non-gravitational acceleration, and the assumption that jets are propelled by thermal outgassing, suggest that 3i Atlas should have lost at least 13% of its total mass during its perihelion passage. This is an enormous amount of material. If the object's nucleus is as large as some estimates suggest, several kilometers in diameter, we are talking about billions of tons of material ejected into space over the course of a few weeks. This mass loss should be visible. It should produce a massive cloud of gas and debris surrounding the nucleus, detectable by spectroscopy and visible in high-resolution imaging. The coming weeks will be critical in testing this prediction. When 3I Atlas reaches its closest approach to Earth on December 19th, we will have our best opportunity to characterize this debris cloud and determine whether the mass loss is consistent with natural outgassing, or whether something else might explain the observed acceleration. If we do not see the expected debris cloud, if the non-gravitational acceleration occurred without the corresponding mass loss that natural processes would require, then we face a significant puzzle. The acceleration would need an alternative explanation, and the most obvious alternative, a propulsion system that does not rely on expelling large quantities of mass, pushes us toward conclusions that most scientists remain deeply reluctant to consider. The amateur astronomy community has played a remarkable role in documenting these jet features. With telescopes ranging from 8 inches to nearly half a metre in aperture, private observers around the world have captured images of 3I Atlas that in some cases exceed the detail shown in official NASA releases. This is not a criticism of NASA. The agency's various spacecraft were designed for other purposes and happened to catch glimpses of 3I Atlas as a target of opportunity. But the contrast between the sharp jet structures captured by dedicated amateur observers and the fuzzy point source images released by NASA has fueled speculation about what additional data might exist that has not been publicly shared. On November 16th, Japanese astrophotographer Satoru Murata captured what many consider the definitive post-perihelion image of 3I Atlas. Using a modest 8-inch telescope in New Mexico, his 24-minute composite exposure revealed the full complexity of the jet structure, multiple sunward and anti-sunward features, a tightly collimated primary tail extending for millions of kilometers, and a bright central condensation that hinted at a compact, well-defined nucleus. One day later, French astronomer François Kugel captured a similar image using a 16-inch telescope, confirming that the structures seen by Murata were real and persistent. The consistency between these independent observations, made from different continents using different equipment, rules out instrumental artifacts or processing errors. Whatever 3I Atlas is doing it consistently, and it is doing it in ways that challenge our expectations. The question that haunts these observations is simple to state but difficult to answer. Are we looking at the most unusual natural comet ever observed, an object whose quirks of composition and geometry produce behaviours at the extreme edge of what natural processes can achieve? Or are we looking at something else entirely, something that only resembles a comet because it has accumulated ice and dust during its journey through the cold spaces between stars? The jets themselves cannot answer this question definitively. They are consistent with both interpretations, with natural processes pushed to unusual extremes, and with technological activity masked by cometary camouflage. What we need is more data, specifically spectroscopic data, that can reveal the velocity and composition of the material in these jets. If the jets are natural outgassing, the material should be moving at thermal velocities, a few hundred meters per second at most. The spectral lines should be broadened by this velocity in predictable ways, and the composition should match what we expect from sublimating ices, primarily water, carbon dioxide, carbon monoxide, and various trace species. If the jets are something else, the spectral signatures could be dramatically different. Higher velocities would produce different line broadening. Unusual compositions might indicate processed materials rather than primordial ices, and certain spectral features associated with high-temperature plasmas might appear if we are looking at thruster exhaust rather than sublimating frost. The Hubble and Webb space telescopes have the capability to obtain these measurements. Ground-based observatories equipped with high-resolution spectrographs could contribute as well. The data may already exist, collected during observation campaigns over the past several months. What we await is the analysis and publication of these results. December brings 3I Atlas closer to Earth than it has been since its discovery. The viewing geometry improves, the object remains active, and the scientific community has had months to prepare observing strategies specifically designed to address the anomalies that have accumulated since July. What those observations reveal will shape our understanding not just of this particular object, but of what kinds of things might wander between the stars. The jets that refuse to blur are either telling us something profound about cometary physics at the extremes, or they are telling us something profound about what else might be out there. Either answer changes how we see the cosmos. The hidden perihelion. There is a moment in every comet's journey through the inner solar system when it becomes invisible to us, when its path carries it behind the Sun and Earth-based telescopes. Can only wait for it to emerge on the other side. For most comets, this solar conjunction is a minor inconvenience, a gap in our observational coverage that we fill in afterward by interpolating between the data collected before and after. For 3i Atlas, the timing of this invisibility was extraordinary. On October 29th, 2025, this interstellar visitor reached perihelion, its closest approach to our Sun, at a distance of approximately 203 million kilometres. This was the moment of maximum solar heating, the point at which any volatile ices would sublimate most vigorously, when the object would be at its brightest and most active. It was precisely the moment when detailed observations would be most scientifically valuable, and it was precisely the moment when 3i Atlas was positioned on the opposite side of the Sun from Earth. The probability that a randomly arriving interstellar object would reach perihelion at the exact time of solar conjunction, hidden from our most powerful ground-based telescopes at the most critical phase of its passage, has been calculated at approximately 1 in 20,000. This is not the most improbable aspect of 3i Atlas, but it is another entry on a growing list of coincidences that individually might be dismissed, but collectively begin to strain credulity. What happened during those hidden weeks? We have some data. NASA's fleet of solar observing spacecraft positioned at various points around the Sun caught glimpses of 3i Atlas as it passed through their fields of view. The Stereo mission, the SOHO observatory, the punch instruments all detected the object, though at considerable distances and with limited resolution. What they recorded was surprising. 3i Atlas brightened rapidly as it approached the Sun, far more rapidly than standard cometary models predicted. The brightness increased as an inverse power of distance to approximately negative 7.5, a steeper relationship than the typical negative 4 to negative 6 observed in most comets. This accelerated brightening suggested that something unusual was happening as solar heating intensified. The object also changed colour. Observations in late October indicated that 3i Atlas had become distinctly bluer than the Sun itself, a startling transformation that contradicts what we expect from dusty cometary surfaces. Dust scatters sunlight preferentially at longer wavelengths, producing a reddening effect. This is why Mars appears red, why sunset skies turn orange and crimson. A comet's coma should appear redder than the illuminating sunlight, not bluer. Several explanations have been proposed. Ionized carbon monoxide produces blue emission and might dominate the coma under intense solar heating. The rapid sublimation of surface materials might have exposed fresher, more reflective ices that scatter blue light more efficiently. Or something else might have been happening, something that produced blue light through mechanisms unrelated to scattered sunlight. A hot engine, to state the obvious, would glow. The exhaust of a rocket motor reaches temperatures of thousands of degrees. Ion thrusters produce energetic plasmas. Either would emit light across the spectrum with a specific colour depending on the materials involved and the temperatures achieved. A technological propulsion system activating at perihelion would produce exactly the kind of anomalous brightness and colour changes that were observed. This is speculation. I want to be clear about that. The blue coloration could have entirely natural explanations rooted in unusual cometary chemistry. But the timing is noteworthy. The anomalous brightening occurred precisely when the object was hidden from detailed Earth-based observation, and precisely when the measured non-gravitational acceleration indicated that something was pushing 3i Atlas off its purely gravitational trajectory. The non-gravitational acceleration detected during perihelion represents perhaps the most significant data point we have about what happened behind the Sun. David Farnokia at NASA's Jet Propulsion Laboratory filed the report based on precise positional measurements from the Atacama Large Millimeter Array. When 3i Atlas emerged from solar conjunction, it was not quite where it should have been if gravity alone had determined its path. It had deviated by approximately 4 arc seconds. a tiny angle, but one that corresponds to a real spatial displacement of meaningful magnitude. The measured acceleration had two components: a radial push away from the Sun of approximately 135 km per day squared, and a transverse component of roughly 60 km per day squared. These are small numbers in absolute terms, but integrated over the weeks of the perihelion passage, they produced a trajectory change that would have significant effects over the subsequent months of travel. Specifically, they produced the trajectory change needed to bring 3I Atlas to Jupiter's Hill radius with remarkable precision. Let me walk through the mathematics because this is important. Before perihelion, based on observations from July through September, the predicted closest approach to Jupiter in March 2026 was not quite at the Hill radius boundary. The non-gravitational forces measured during the hidden perihelion passage adjusted this prediction. The new trajectory incorporating these forces now brings 3I Atlas to within 60,000 kilometers of the exact Hill radius value. The adjustment was not random in direction. It was not random in magnitude. It was precisely what was needed to achieve the Hill radius match. Not more, not less. Exactly right. If 3I Atlas is a natural comet experiencing outgassing, this precision is an astonishing coincidence. The gases sublimating from its surface just happened to push in the right direction by the right amount to produce this specific outcome. The universe rolled the dice and came up with the exact number needed. If 3I Atlas is technological, this precision is expected. A course correction at perihelion makes perfect sense. It is the optimal point for manoeuvres because the object is moving fastest, deep in the Sun's gravity well, where small thrust produces maximum trajectory change. This is called an Oberth maneuver, and we use it routinely in our own space missions. A probe adjusting its trajectory to reach a specific target would fire its engines at perihelion, and it might prefer to do so while hidden from observation. The weeks following perihelion have provided additional data that bears on this question. 3I Atlas emerged from solar conjunction still active, still producing jets, still behaving in ways that challenge conventional cometary models. The mass loss required to explain the observed non-gravitational acceleration through natural outgassing should have been substantial, at least 10 to 13% of the total nucleus mass based on Professor Loeb's calculations. If this mass was ejected as gas and dust, it should still be visible. It should form a vast expanding cloud surrounding the nucleus, detectable spectroscopically and visible in high-resolution imaging. The coming weeks of observation will be critical in determining whether this predicted debris cloud exists. Some early indications are puzzling. Amateur images from mid-November show a surprisingly compact nucleus, with relatively little diffuse material surrounding it. The jets are prominent but collimated, not the diffuse expanding shells we might expect from massive outgassing. The overall appearance is of an object that has remained more intact than the mass loss calculations would suggest. This could simply mean that our estimates of the mass loss are wrong, that the non-gravitational acceleration has a different explanation than we assumed. Perhaps the outgassing was more directed than typical, more efficient at producing thrust with less total mass expelled. Perhaps the composition of 3I Atlas differs from standard cometary materials in ways that affect the relationship between sublimation and acceleration. Or perhaps the acceleration did not come from outgassing at all. The Hubble Space Telescope and the James Webb Space Telescope both observed 3I Atlas before perihelion. The data from those observations is still being analysed. What we know so far indicates an object with unusual properties, a coma dominated by carbon dioxide rather than water, chemical abundances that differ from solar system comets, a structure and activity pattern that set it apart from anything we have seen before. What we need now is post-perihelion data of comparable quality. We need spectroscopy of the jets to determine their velocity and composition. We need high-resolution imaging to characterize the debris cloud or confirm its absence. We need continued precision tracking to refine the trajectory and confirm whether the Hill radius coincidence holds as our measurements improve. December 19th is circled on many astronomers' calendars. That date marks the closest approach of 3I Atlas to Earth, approximately 269 million kilometers. Still a vast distance by everyday standards, but close enough for our most powerful instruments to gather data impossible to obtain at greater range. The object will be climbing higher in the pre-dawn sky for Northern Hemisphere observers. Ground-based telescopes from Hawaii to the Canary Islands will have their best viewing conditions. space telescopes will point their mirrors at this interstellar wanderer for what may be our final opportunity to study it in detail before it continues outward toward Jupiter and beyond. What happens after December 19th is largely out of our hands. 3i Atlas will continue on its trajectory, receding from the Sun, cooling, presumably becoming less active as the solar heating that drives cometary processes diminishes. By the time it reaches Jupiter in March 2026, it may have faded to the point where only the largest telescopes can detect it. But Juno will be watching, the spacecraft that has orbited Jupiter since 2016, studying the gas giant's atmosphere and magnetosphere, will have a front-row seat for whatever happens when 3i Atlas grazes the boundary of Jupiter's gravitational domain. Its instruments can detect things that Earth-based telescopes cannot, from magnetic field perturbations to energetic particle emissions to close-up imaging unavailable from our distant vantage point. The hidden perihelion gave 3i Atlas the opportunity to do whatever it did without our watching. The Jupiter encounter will not offer the same privacy. We will be observing, we will be recording, and whatever happens at the edge of the Hill sphere will be documented for analysis. The waiting is the hardest part. We have tantalizing data, suggestive anomalies, statistical improbabilities that accumulate like snowflakes into something that feels increasingly difficult to dismiss. But we do not have proof of anything extraordinary. We have a mystery, a genuine scientific puzzle that current models struggle to explain. The next few months will either deepen that mystery or resolve it. Either 3i Atlas will continue to defy our expectations, adding new anomalies to the list, strengthening the case that something unusual is happening. Or it will settle into patterns we recognize, revealing itself as a remarkable but ultimately natural object, a comet from another star whose peculiarities stem from its exotic origin rather than its exotic nature. Both outcomes advance our knowledge, both outcomes are scientifically valuable, but one outcome would change everything we think we know about our place in the cosmos. What happened behind the Sun during those hidden weeks of October? The data we have raises more questions than it answers. The data we collect in December and March may finally tell us whether those questions have ordinary answers or extraordinary ones. What NASA did not say on November 19, 2025, NASA held a press conference that had been anticipated for weeks. The agency's associate administrator, Amit Kshatriya, stood before cameras and delivered a message that seemed designed to close a door that many felt should remain open. His words were direct. This object is a comet. It looks and behaves like a comet. All evidence points to it being a comet. The timing of this statement was significant. For 42 days, from October 1st through November 12th, the United States government had been shut down. During precisely the period when 3i Atlas was passing behind the Sun, when the most critical observations should have been collected and analysed, NASA's workforce was largely furloughed. Data accumulated on spacecraft hard drives, analysis waited, and speculation flourished in the vacuum. When the agency finally emerged from the shutdown and scheduled its press conference, expectations were high. What had the Mars orbiters seen during the close approach in early October? What had the solar observatories recorded during perihelion? What did the spectroscopic data reveal about the composition and structure of this interstellar visitor? The answers provided were disappointing to many. The centerpiece of NASA's presentation was an image from the high-rise camera aboard the Mars Reconnaissance Orbiter, captured when 3i Atlas passed within approximately 30 million kilometers of the red planet. HiRISE is one of the most powerful cameras ever sent to another world. It can resolve features on the Martian surface down to about 30 centimeters across. Pointed at 3i Atlas from a distance of 30 million kilometers, it should have achieved a pixel resolution of roughly 30 kilometers. What was shown was a fuzzy blob. The image, a 3.2-second exposure, showed a smeared point of light with arrows indicating the directions of the Sun and the object's motion. Spacecraft jitter during the observation had spread the light across several pixels. The coma appeared compact, perhaps 1,500 kilometers across, but no fine detail was visible. No jets, no structure, nothing that would address the anomalies that had been accumulating since July. Professor Loeb's response was sharp. He quoted Arthur Conan Doyle's Sherlock Holmes. There is nothing more deceptive than an obvious fact. His criticism focused not on what NASA presented, but on what NASA did not discuss. The 12 anomalies he had catalogued, the statistical improbabilities, the jets observed by amateur astronomers, the non-gravitational acceleration, the Hill radius coincidence. None of these received mention. Instead, officials repeated what Loeb called the official mantra: "It is a comet. It is natural." There is nothing unusual here. The contrast between NASA's messaging and the data available from other sources was stark. On the same days that NASA was presenting its fuzzy, high-rise image, amateur astronomers with backyard telescopes were capturing dramatically more detailed views of 3I Atlas. Images showing multiple collimated jets, complex coma structure, the distinctive anti-tail. How could 8-inch telescopes in New Mexico produce sharper images than a spacecraft specifically designed for high-resolution imaging? The answer lies in what each instrument was designed to observe. HiRISE was built to photograph the Martian surface from orbit, a relatively nearby target moving at known speeds along predictable paths. Pointing it at a fast-moving distant comet required compromises. The exposure time needed to gather enough light also allowed spacecraft motion to blur the image. The instrument was not optimized for this task. But this explanation, while technically accurate, does not fully address the criticism. NASA has other assets. The Mars Atmosphere and Volatile Evolution Orbiter, MAVEN, captured ultraviolet images that would help characterize the hydrogen envelope around 3I Atlas. The Perseverance rover on the Martian surface photographed the comet against the dusty Martian sky. Multiple solar observatories recorded the object during its perihelion passage. Where is that data? The agency acknowledged that additional analysis was ongoing. Data from the Webb telescope's August observations, which should provide detailed spectroscopy of the coma composition, was described as still being processed. Data from various solar observatories was mentioned but not shown. The impression left by the press conference was of an agency presenting the minimum necessary to address public interest, while withholding the more detailed results for later publication through official scientific channels. This is how science normally works. Data is collected, analysed carefully, peer-reviewed, and published in journals where other scientists can examine the methodology and conclusions. The process takes time, it ensures quality, it prevents premature claims based on incomplete analysis. But 3I Atlas is not a normal scientific subject. Public interest is intense, speculation is rampant, and the data being withheld could potentially address questions that millions of people are asking. In this context, NASA's cautious approach has fueled exactly the kind of conspiracy thinking that the agency presumably wants to avoid. Congresswoman Anna Paulina Luna of Florida had already written to NASA Administrator Sean Duffy, demanding the release of Mars orbiter images. She spoke with Professor Loeb by phone and expressed concern about transparency. Whether her intervention accelerated NASA's press conference or influenced its content is unclear. But the fact that congressional representatives are now involved indicates how far beyond normal scientific discourse this story has travelled. What did NASA actually say during the press conference, beyond the headline assertion that 3I Atlas is a comet? Officials described the object as actually pretty amazing as comets go, being the oldest ever seen and the most massive of its kind. They attributed its unusual characteristics to its extrasolar origin, suggesting that formation in a different stellar environment could explain properties that differ from solar system comets. They emphasized that all observed behaviors are consistent with natural processes, even if those processes are operating in unfamiliar ways. This framing is scientifically defensible. 3I Atlas did form around another star. It has spent billions of years in interstellar space. Its composition and structure could legitimately differ from objects that formed in our own solar neighbourhood. Unusual does not mean unnatural, but the framing also sidesteps the specific anomalies that have driven public interest. The retrograde trajectory aligned with the ecliptic, the arrival time fine-tuned for planetary encounters while avoiding Earth observation at perihelion. The anti-tail confirmed by Mars imaging to be a genuine physical structure rather than a perspective illusion. The non-gravitational acceleration measured at precisely the magnitude needed for the Hill radius match. The jets that maintain collimation despite rotation. None of these received detailed discussion. None were explained in the context of natural cometary physics. They were simply not mentioned. Professor Loeb characterized this as a missed opportunity for public outreach. When communicating to the public, he argued, you should not downgrade the mystery, but emphasize it. The public cares about puzzles, about questions without easy answers. An agency that insists nothing unusual is happening when the data suggests otherwise risks appearing defensive, possibly deceptive. The amateur astronomy community has responded with intensified observation campaigns. If NASA will not provide high-resolution data, citizen scientists will generate their own. Networks of observers coordinating across continents have produced a stream of images documenting the post-perihelion evolution of 3i Atlas, with a detail that often exceeds official releases. This democratization of observation is unprecedented. Never before have amateurs played such a prominent role in studying a major astronomical phenomenon. The gap between professional and amateur capabilities has narrowed dramatically as telescope technology has improved and image processing software has become more sophisticated. A dedicated amateur with a 20-inch telescope and good seeing conditions can now produce scientific quality data that advances our understanding of objects like 3i Atlas. The question is what we do with that data. The images showing multiple jets and unusual structure are available for anyone to examine. They are posted on astronomy forums, shared on social media, analysed in blog posts and YouTube videos. Professional scientists can download them and apply rigorous analysis. The data is not hidden. What is hidden, at least for now, is the professional data that could confirm or contradict what amateur observers are seeing. The Webb spectroscopy, the full HiRISE dataset, the MAVEN ultraviolet observations, the precision tracking data that refines the trajectory predictions. This information exists. It will eventually be published. But in the meantime, we are left with official assurances that conflict with the visual evidence available to anyone with internet access. NASA's position is that 3i Atlas is a natural comet displaying unusual but explicable behaviours. Professor Loeb's position is that the accumulation of anomalies has reached a point where alternative explanations deserve serious consideration. Both positions are defended by smart people examining the same data. The disagreement is not about facts, but about interpretation, about how many coincidences are required before coincidence becomes an inadequate explanation. The coming weeks will provide more data. December observations will either reinforce NASA's natural comet narrative or strengthen the case for something stranger. The March encounter with Jupiter will offer a definitive test of the Hill radius prediction. Until then, we have questions without answers and assurances that many find unconvincing. We have amateur images showing structures that official imagery does not reveal. We have a press conference that seemed designed to close discussion rather than advance understanding. And we have an interstellar visitor continuing its journey toward Jupiter, carrying secrets that may or may not be revealed before it disappears forever into the outer darkness. The chemical fingerprint. Every object in the universe carries a chemical signature, a fingerprint written in the spectral lines of the light it emits or reflects. When we pass that light through a spectrograph, spreading it into its component wavelengths, we can read that signature like a barcode, identifying which elements and molecules are present and in what abundances. This technique has allowed us to determine the composition of stars thousands of light years away, of galaxies at the edge of the observable universe, of comets passing through our solar system on their way to oblivion. When astronomers turned their spectrographs toward 3i Atlas, what they found was not what they expected. The European Southern Observatory's Very Large Telescope captured spectra of 3i Atlas in the weeks before perihelion. Among the emission lines detected was a strong signal from nickel, one of the heavier elements produced in stellar cores and distributed through space by supernova explosions. Nickel is not unusual in comets. What was unusual was the ratio. In most solar system comets, nickel and iron appear together in roughly solar proportions, meaning the ratio between them matches what we observe in the Sun and throughout our cosmic neighbourhood. These elements are released from organometallic compounds that sublimate at relatively low temperatures, contributing to the gaseous coma that surrounds an active comet. The physics and chemistry are well understood. In 3i Atlas, the nickel signal was strong. The iron signal was weak. The ratio was dramatically different from anything observed in the thousands of comets we have studied over decades of spectroscopic observation. This is not merely a curiosity. The nickel-to-iron ratio is a diagnostic of formation conditions. It tells us about the temperature, pressure, and chemical environment where the material in question was assembled. A ratio dramatically different from solar values suggests formation in an environment dramatically different from our own solar system. Or it suggests something else entirely. High nickel, low iron alloys have industrial applications. They resist corrosion and maintain strength at high temperatures. Inconel, a family of nickel-based superalloys, is used in aerospace applications, including rocket engines. Manel, another nickel alloy, is valued for its resistance to saltwater corrosion and is used in marine applications and chemical processing equipment. This is not to suggest that 3I Atlas is made of Inconel. The spectroscopic detection measures gaseous nickel and iron in the coma, not the solid composition of the nucleus. But the gas phase abundances reflect what is sublimating from the surface, which in turn reflects the bulk composition of the object. An unusual gas phase ratio implies unusual solid phase composition. Professor Loeb listed this as one of the anomalies supporting a non-natural interpretation. The probability that a random interstellar comet would display nickel to iron ratios resembling industrial alloys rather than natural abundances is low. Not zero, but low enough to add weight to the accumulating pile of coincidences. The counterargument is that we have a sample size of 1. 3I Atlas is only the third interstellar object ever detected, and the first two, Oumuamua and Borisov, provided limited or no spectroscopic data on heavy element abundances. We simply do not know what the normal range of nickel to iron ratios looks like for interstellar objects. Perhaps 3I Atlas is typical of its class. Perhaps the exotic formation environments around other stars routinely produce these unusual ratios. We cannot say with confidence that the observation is anomalous when we have no baseline for comparison. This is a fair point. The absence of comparison data makes interpretation difficult, but it also means we cannot dismiss the unusual ratio as falling within normal variation. It could be normal for interstellar objects. It could also be diagnostic of something far more interesting. The nickel anomaly was not the only compositional surprise. The James Webb Space Telescope observed 3I Atlas in August 2025 using its near-infrared spectrograph. The results, still being fully analysed, indicated a coma dominated by carbon dioxide rather than water. This is unusual for comets observed in the inner solar system, where solar heating typically drives water ice sublimation as the primary activity. Carbon dioxide sublimates at lower temperatures than water, meaning it can drive cometary activity even at greater distances from the Sun. Long-period comets making their first passage through the inner solar system sometimes show carbon dioxide-dominated comas because their water ice has not yet been heated sufficiently to sublimate. But 3I Atlas was observed at distances where water should have been active. The carbon dioxide dominance suggests either that water is depleted relative to carbon dioxide, or that water is somehow inhibited from sublimating. The Webb data indicated that water comprised only about 4% of the coma by mass. This is extraordinarily low. Most active comets show water as the dominant volatile, often comprising 50% or more of the outgassing products. Either 3I Atlas formed with very little water ice, or something has removed or sequestered the water that should be present. Formation in a very cold environment, far from the host star, might explain carbon dioxide dominance. At temperatures below the sublimation point of water, carbon dioxide ice would be stable, while water ice would freeze out of the gas phase. An object forming in such conditions might be enriched in carbon dioxide relative to water. But other interstellar objects and long-period comets do not show this extreme carbon dioxide dominance. 2I Borisov, the second interstellar object, displayed a coma composition broadly similar to solar system comets. Why would 3I Atlas be so different? The Webb observations also detected molecular nitrogen at levels higher than typically seen in comets. Nitrogen ice is extremely volatile, sublimating at even lower temperatures than carbon dioxide. Its presence suggests that 3I Atlas has spent most of its existence at very cold temperatures, preserving ices that would have been lost from objects with warmer histories. This is consistent with the estimated age of the object. Analysis of its trajectory and the stellar populations it might have originated from suggests 3I Atlas could be 7 billion years old, significantly older than our own solar system, an object that ancient would have spent immense periods in the cold of interstellar space, far from any stellar heat source. Volatile preservation would be expected, but age alone does not explain the specific ratios observed. billions of years in interstellar space would affect all ices similarly. It would not selectively deplete water while preserving carbon dioxide and nitrogen. Something about the formation conditions, the original composition, differs from what we consider typical. The chemical fingerprint of 3I Atlas paints a picture of an object that is genuinely exotic, formed in conditions different from our solar system, enriched in unusual volatiles, depleted in expected species, carrying heavy element ratios that match no known natural population. Each of these observations has potential natural explanations. Different stellar environment, different formation temperature, different processing history. The universe is vast and varied, and we should expect objects from other systems to differ from our local examples. But the accumulation is striking. It is not just one unusual property. It is a suite of them, all present in the same object, all pointing toward formation and processing conditions we have never encountered before. Either the diversity of interstellar objects far exceeds what we imagined, or 3I Atlas is telling us something beyond mere compositional variation. The spectroscopic data collected in December will be crucial. As 3I Atlas reaches its closest approach to Earth, conditions for detailed spectroscopy improve dramatically. Higher signal-to-noise ratios will allow detection of fainter spectral features. Comparison of coma composition before and after perihelion will reveal how solar heating has affected the object. Changes in relative abundances could indicate ongoing processing or differentiation. Particularly important will be spectroscopy of the jets. If we can isolate light from the collimated structures documented by amateur observers, we can measure their composition and velocity directly. Are the jets made of the same material as the ambient coma? Are they moving at thermal velocities consistent with natural sublimation? Are there spectral signatures of unusual excitation or ionization? The answers to these questions could resolve much of the current uncertainty. Natural cometary jets should show specific signatures, predictable velocities, expected compositions. Technological propulsion would show something different, higher velocities, unusual ionization patterns, possibly spectral features associated with specific fuel or propellant chemistry. We have the instruments to make these measurements. What we lack is time. 3I Atlas is receding from the Sun, cooling, presumably becoming less active as the driving heat diminishes. The window for high-quality spectroscopy is measured in weeks, not months. Every clear night at a major observatory is precious. The chemical fingerprint already tells us that 3I Atlas is extraordinary. What we do not yet know is whether that extraordinariness stems from exotic natural origins or from something more provocative entirely. The spectrographs will speak. Whether we are prepared to listen to what they say is another matter. The backyard revolution. There is something remarkable happening in astronomy right now, something that inverts the traditional hierarchy of who gets to make discoveries and who gets to wait for official announcements. For decades, the paradigm was clear. Professional astronomers with access to billion-dollar telescopes made the observations. They analysed the data behind closed doors. They published their findings in peer-reviewed journals, and the rest of us learned what they chose to tell us, when they chose to tell us. 3I Atlas has disrupted this paradigm in ways that will likely have lasting effects on how astronomical discoveries are communicated and understood. Consider the image captured by Satoru Murata on November 16th. Using a Celestron Edge HD 800, a telescope with a primary mirror just 8 inches across, operating from a remote observatory in New Mexico, Murata produced a composite image of 3I Atlas that revealed structural details invisible in any NASA release to that date. Multiple jets extending in various directions. A tightly collimated primary tail stretching for millions of kilometers. The distinctive anti-tail structure that had been a point of controversy since summer. How is this possible? How can a telescope that costs perhaps $10,000 produce sharper images than spacecraft costing hundreds of millions? Part of the answer lies in integration time and purpose. The Mars Reconnaissance Orbiter's high-rise camera captured 3I Atlas in a brief exposure while the spacecraft was moving relative to the target. The image was a snapshot, limited by spacecraft motion and pointing stability. Murata's image combined 24 separate 60-second exposures, carefully aligned and stacked to build up signal while averaging out noise. The total integration time was nearly half an hour, orders of magnitude longer than any single spacecraft exposure. But integration time is only part of the story. Ground-based observers have another advantage that is often overlooked. They can optimize specifically for the target they are imaging. A spacecraft in orbit around Mars is designed for many purposes. Its cameras are configured to image the Martian surface, track dust storms, photograph the moons. Turning those instruments toward an unexpected target like an interstellar comet requires compromises. The instrument is not optimized for the task. Amateur astronomers face no such constraints. When Elena Walter pointed her 17-inch telescope at 3i Atlas from an observatory in Chile, she could configure every aspect of the observation for that specific target. Exposure time, filter selection, tracking rate, all could be adjusted to maximize data quality for this one object. The result was imagery that complemented and in some cases exceeded what professional facilities were releasing. The amateur astronomy community has embraced 3i Atlas as perhaps no other object in recent memory. Online forums buzz with observation reports, processing techniques, comparative analysis of images taken from different continents on the same nights. Citizen scientists are coordinating global campaigns, sharing data freely, building collective understanding of an object that professional astronomers have been relatively slow to characterize publicly. This bottom-up approach to discovery has yielded significant insights. The complex jet structure documented in mid-November was first identified and mapped by amateur observers. The persistence of the anti-tail across multiple weeks was confirmed through amateur observation networks before any professional confirmation was published. The gradual evolution of the coma structure as 3i Atlas receded from the Sun has been tracked in detail by observers with no professional affiliation. Professional astronomers are paying attention. Professor Loeb has repeatedly cited amateur images in his blog posts and interviews, noting that citizen scientists have produced data more illuminating than official NASA releases. The images are real, the structures they show are real, and they demand explanation regardless of who captured them. There is tension inherent in this situation. Professional science operates through peer review, through careful verification, through institutional credibility built over decades. Amateur observation, however skilled, lacks these formal structures. An image posted to a Facebook astronomy group does not carry the same authority as a publication in Nature or Science. But authority and accuracy are not the same thing. The amateur images of 3i Atlas are consistent with each other, captured by different observers using different equipment from different locations around the world. They show the same structures, the same evolution over time, the same unusual features. Either dozens of amateur astronomers across multiple continents are all making the same systematic errors, or they are accurately documenting something real. The professional community will eventually catch up. Papers are being written, data is being analysed, the formal scientific literature on 3i Atlas is growing, but in the meantime, the most detailed visual record of this interstellar visitor is being assembled not by NASA or ESA or any national space agency, but by private individuals motivated by curiosity and equipped with technology that would have been unimaginable a generation ago. Consider what this means for future discoveries. The Vera Rubin Observatory, scheduled to begin full operations soon, will detect many more interstellar objects over the coming decade. Each will likely generate the same intense public interest that 3i Atlas has attracted. Each will prompt the same questions about origin, composition, trajectory. And each will be observed not only by professional astronomers, but by a global network of amateur observers capable of generating scientific quality data in near real time. The institutions of professional astronomy will need to adapt. Timely data release becomes more important when the public can generate their own observations for comparison. Transparency about methods and findings becomes more important when independent verification is possible. The old model of hoarding data until publication simply does not work when citizen scientists are already posting their results. 3i Atlas has become a test case for this new paradigm. The disconnect between NASA's conservative public messaging and the dramatic amateur imagery has fueled skepticism about official pronouncements. If the agency is showing us fuzzy blobs while backyard telescopes reveal multiple jets and complex structure, what else might be hidden in the professional data sets? This skepticism may be unfounded. The professional data may ultimately show exactly what amateur observers are seeing, analysed in greater depth and with more rigorous uncertainty quantification. The delay in release may be entirely attributable to the normal pace of scientific analysis, compounded by the government shutdown. There may be no concealment, no hidden agenda, only the standard caution of scientists who prefer to be right rather than first. But perception matters. In an environment where trust in institutions is fragile, where conspiracy theories flourish in information vacuums, the appearance of concealment can be as damaging as actual concealment. NASA's communication strategy around 3i Atlas has created exactly the conditions where alternative narratives thrive. The amateur astronomy community does not need NASA's permission to observe the sky. They do not need official validation to share their images. They do not need peer review to post their data online. This democratization of observation is fundamentally changing how unusual astronomical phenomena are documented and discussed. For 3i Atlas specifically, the amateur record will likely be the most complete visual documentation we have. Professional observations are deeper, more quantitative, more scientifically rigorous. But amateur observations are more numerous, more continuous, more immediately available. When historians look back at the passage of the third interstellar object through our solar system, they will draw heavily on the citizen science record. Some of the most striking images have come from unexpected quarters: a retired engineer in Belgium, a software developer in Japan, a medical professional in France who photographs the sky as a hobby. These individuals, with no formal astronomical training, have contributed meaningfully to our understanding of one of the most unusual objects ever to visit our solar system. The democratization of astronomy is not complete, and it never will be. Space-based observations remain the exclusive province of well-funded agencies. Radio astronomy requires facilities beyond any private budget. Spectroscopy at professional quality demands resources most amateurs cannot access. But within the domain of optical imaging, the playing field has leveled dramatically. 3i Atlas has demonstrated what that leveling means in practice. When official channels are slow, citizen scientists fill the gap. When professional data is withheld, amateur data flows freely. When institutions say nothing unusual is happening, observers can check for themselves. This is a healthy development for science and for society. It keeps institutions honest. It distributes the power of discovery more broadly. It engages the public directly in the scientific enterprise, rather than positioning them as passive consumers of official truth. The backyard telescopes pointed at 3i Atlas tonight are writing a chapter in the democratization of knowledge. Whatever this object turns out to be, the process of discovering its nature has already changed, because ordinary people refused to wait for permission to look up. The Juno Gambit. There was a moment in early September 2025 when a decision was made that may haunt astronomical history. NASA's Juno spacecraft, orbiting Jupiter since 2016, had a window of opportunity. A carefully calculated manoeuvre, a burn of its main engine delivering roughly 2.7 kilometers per second of velocity change, could have redirected the spacecraft from its current orbit around Jupiter to intercept the path of 3i Atlas as the interstellar visitor approached the gas giant. That window closed without action. The proposal came from a team led by Professor Loeb, working with trajectory specialists Adam Hibbard and Adam Crowell. Their calculations, published in a peer-reviewed paper, demonstrated that the mathematics were favourable. Juno had fuel remaining. The required velocity change was within the spacecraft's capability. The timing aligned with what was then the planned end of Juno's extended mission. The potential rewards were substantial. Juno carries a suite of instruments designed to study Jupiter's atmosphere and magnetosphere, instruments that could be repurposed to examine 3i Atlas from a distance impossible to achieve from Earth. The spacecraft's Juno cam could image the object at resolutions far exceeding any ground-based telescope. Its spectrometers could analyse the composition of the Comet and jets. Its magnetometer could detect any magnetic field associated with the object. Its particle detectors could sample material in the extended debris cloud surrounding the nucleus. Even a distant flyby, at ranges of tens of millions of kilometres, would have provided data qualitatively different from anything available through Earth-based observation. We would have had a perspective from the outer solar system, seeing 3i Atlas from an angle impossible from our vantage point near the Sun. We would have had measurement capabilities calibrated for deep space conditions. We would have had eyes on the target during the critical weeks when it approaches Jupiter's hill sphere. Instead, Juno, continues its orbit around Jupiter, still returning valuable data about the gas giant, still operating within its original mission parameters. The opportunity to intercept 3I Atlas was evaluated and declined. Why? The public explanation involves several factors. Juno's engine has not been fired since 2017. Concerns about the propulsion system, specifically the pressurization of the fuel tanks, led to cancellation of a planned orbit change maneuver years ago. Whether the engine would reliably fire after 8 years of dormancy was uncertain. A failed maneuver could have ended the mission prematurely. Additionally, redirecting Juno would have meant abandoning the planned observations of Jupiter that constituted its primary mission. The spacecraft's remaining lifetime would have been consumed by the transfer trajectory rather than by continued science at Jupiter. Trading certain continued observations for an uncertain intercept with a controversial target was not obviously worthwhile from a mission management perspective. There were also political considerations. The proposal came from Professor Loeb, whose advocacy for considering technological explanations for anomalous objects has made him a controversial figure within the astronomical establishment. Endorsing his intercept proposal could be seen as lending credibility to interpretations that NASA had been careful to distance itself from. The result is that we will observe the Jupiter encounter from Earth, augmented by whatever distant observations Juno and the European Space Agency's JUICE spacecraft can provide from their respective positions near the gas giant. These observations will be valuable. They will not be as valuable as what an intercept mission could have achieved. The Juno gambit illustrates a broader tension in space science between cautious institutional management and bold opportunistic response. Interstellar objects are rare. 3I Atlas is only the third ever detected. The next one might not arrive for years or decades. When an opportunity presents itself, when the orbital mechanics align favourably, and an existing spacecraft could be repurposed, the case for action seems compelling. But spacecraft are expensive. Missions are planned years in advance. The institutional machinery of space agencies is not designed for rapid pivots to unexpected targets. By the time the proposal was fully evaluated, the window had effectively closed. Congresswoman Luna's letter to NASA advocated for using Juno to observe 3I Atlas. Whether her intervention had any effect on agency planning is unclear. The mission continues on its original trajectory, and the closest approach of 3I Atlas to Jupiter will occur without a spacecraft positioned to intercept it. What might we have learned? Consider the questions that remain unanswered. Are the collimated jets genuine physical structures or imaging artifacts? Juno's cameras could have resolved this, definitively. Is the antitail a beam of particles or something else entirely? Close-range spectrometry could have characterized it. Is there a magnetic field associated with 3I Atlas, as some natural comets display due to interaction with the solar wind? Juno's magnetometer could have detected fields far weaker than any Earth-based instrument. Most importantly, what happens when 3I Atlas reaches the Hill radius? If this object is somehow targeting Jupiter's gravitational sphere of influence, if it intends to release something at the boundary, Juno in an intercept trajectory would have been positioned to observe whatever occurs. From Earth, we will see only what our distant telescopes can resolve. From close range, we might have seen everything. The decision not to redirect Juno will be debated regardless of what 3I Atlas turns out to be. If the object proves to be an unusual but natural comet, critics will say the proposal was never worth the risk. The engine might have failed. The intercept might have produced little data of value. The sacrifice of continued Jupiter observations would have been unnecessary. If the object proves to be something extraordinary, the missed opportunity will take on a different character. We had a spacecraft in position, we had the mathematics worked out, we had the fuel available, and we chose caution over curiosity, institutional inertia over scientific opportunism. The JUICE spacecraft, launched by the European Space Agency and currently en route to Jupiter for arrival in 2031, offers a partial consolation. JUICE observed 3I Atlas in November 2025 from a distance of approximately 64 million kilometres, using cameras and spectrometers designed for planetary science. The data from those observations will be downlinked over the coming months, constrained by the spacecraft's limited communication bandwidth during its current mission phase. JUICE will not intercept 3I Atlas. The spacecraft is on a gravity-assist trajectory that does not pass near the interstellar object's path, but its observations from a different vantage point than Earth, at different phase angles, and with different instrumental sensitivity, will complement ground-based data in valuable ways. The fundamental lesson of the Juno gambit may be about preparedness rather than opportunity. We were not ready for 3i Atlas. Despite decades of discussion about interstellar objects, despite proposals for interceptor missions, despite the experience gained from Oumuamua and Borisov, we had no capability positioned to respond quickly when the third interstellar object appeared. The ESA Comet interceptor mission, currently in development, is designed to address exactly this gap. Stationed at a gravitationally stable point in space, it will wait for an interesting target, either a long-period comet or an interstellar object, and then launch to intercept it. But Comet Interceptor will not be operational until the late 2020s at earliest. It could not have helped with 3i Atlas. Future interstellar visitors will likely receive better treatment. The Vera Rubin Observatory will provide earlier detection, giving more warning time. Advances in propulsion technology may enable faster response. Dedicated interceptor missions like Comet Interceptor will provide purpose-built capability. The lessons learned from 3i Atlas will inform mission design and operational planning. None of this helps with the current situation. 3i Atlas is approaching Jupiter on its own schedule, indifferent to our preparedness or lack thereof. We will observe from the distances available to us, extract what data we can, and wonder what we might have learned if Juno had been sent to meet it. The gas giant looms ahead on the interstellar trajectory. In March 2026, 3i Atlas will graze the boundary of Jupiter's gravitational domain, arriving at the Hill radius with a precision that either represents extraordinary coincidence or extraordinary intent. Juno will be orbiting Jupiter, its instruments pointed at the gas giant's storms and aurora. Perhaps its cameras will catch a glimpse of the visitor passing by. Perhaps its particle detectors will register traces of the extended debris cloud. Perhaps the data will answer questions we cannot currently formulate, or perhaps we will look back at September 2025 as the moment when caution cost us the chance of a lifetime. The Juno gambit was declined, the interstellar object continues its approach, and we are left to observe from afar, wondering what a closer look might have revealed. The December window, December 19th, 2025. Mark the date on your calendar. On that day, 3i Atlas will reach its closest approach to Earth, passing at a distance of approximately 269 million kilometers. Still impossibly far by everyday standards, nearly twice the distance between Earth and the Sun. But for astronomers, this represents our best opportunity to study this interstellar visitor before it continues outward toward Jupiter and eventually into the void beyond. The geometry of planetary motion determines these windows. For months, 3i Atlas travelled along a trajectory that kept it relatively distant from Earth, even as it approached the Sun. Its perihelion passage occurred when the object was on the opposite side of the Sun from our planet. Now, as both Earth and 3i Atlas continue their orbits, the distances are finally decreasing to levels that enable detailed observation. Every major telescope on Earth will be pointed at this target during the December window. The Hubble Space Telescope will capture high-resolution images in multiple wavelengths, resolving structures in the coma and potentially the nucleus itself at levels impossible from ground-based facilities. The James Webb Space Telescope, if allocated observation time, could provide spectroscopic data of unprecedented quality, measuring the composition and velocity of material in the jets and tail. Ground-based giants will contribute as well. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gran Telescopio Canarias in the Canary Islands. Each brings unique capabilities to the campaign. Adaptive optic systems will sharpen images blurred by atmospheric turbulence. Spectrographs will dissect the light into its component wavelengths, revealing chemical fingerprints invisible to imaging cameras alone. What will we look for during this critical period? First, and most importantly, the mass loss question. The non-gravitational acceleration measured during perihelion implies substantial outgassing if natural processes are responsible. Calculations suggest 3i Atlas should have ejected at least 13% of its total mass to produce the observed trajectory change through sublimation alone. This material should still be present, expanding outward from the nucleus in a vast cloud of gas and dust. If we see this cloud, if spectroscopy reveals billions of tons of recently ejected material surrounding the nucleus, The natural comet hypothesis is strongly supported. The anomalous acceleration finds an explanation consistent with conventional physics. The mystery, while not entirely resolved, becomes less mysterious. If we do not see this cloud, if the nucleus appears more compact than the mass loss calculations predict, we face a puzzle. The acceleration happened. Something pushed 3I Atlas off its gravitational trajectory. If that something was not massive outgassing, what was it? Second, the jet characterization. The collimated jets, documented by amateur astronomers since early November, have been one of the most striking features of 3I Atlas. December observations with professional-grade spectrographs can measure the velocity of material in these jets directly. Thermal outgassing produces gas moving at hundreds of meters per second. Technological propulsion produces exhaust at kilometers per second. The spectral line widths will distinguish between these scenarios. Additionally, composition measurements of the jets versus the ambient coma could reveal whether the jets are simply concentrated versions of the general outgassing, or whether they represent something compositionally distinct. A natural comet would show similar abundances throughout. A spacecraft using propellant would show jet composition differing from whatever surface ices might also be sublimating. Third, nuclear morphology. The Hubble Space Telescope can resolve features at scales of tens of kilometers at the distance of closest approach. This is not fine enough to see surface detail on a nucleus a few kilometers across, but it is fine enough to determine whether we are looking at a single, coherent object or multiple fragments. It is fine enough to characterize the shape of the inner coma and detect any asymmetries that might indicate unusual activity patterns. Some have speculated that 3I Atlas might fragment as it recedes from the Sun, releasing smaller objects that could follow divergent trajectories. If this is a natural comet experiencing stress from outgassing and thermal cycling, fragmentation is possible. If this is something else, fragmentation might occur as components separate for different purposes. High-resolution imaging during the December window would document either scenario. Fourth, photometric monitoring. The brightness of 3I Atlas tells us about its activity level, and brightness variations over time can reveal rotation, outbursts, and structural changes. Professional and amateur observers will track the light curve continuously during December, building a detailed record of how the object evolves as it recedes from solar heating. Unexpected brightness changes would be particularly significant. A sudden flare might indicate an outburst event, new material exposed to sunlight for the first time. A sudden dimming might indicate that a major active region has rotated out of view or that outgassing has diminished more rapidly than expected. Either would provide constraints on models of the object's structure and activity. The Virtual Telescope project has announced a live observing session for December 19th itself, streaming real-time images of 3I Atlas at its closest approach. Viewers around the world will be able to watch as professional telescopes track this interstellar wanderer, seeing the data as it is collected, participating virtually in what may be the final extended observation window before the object fades into the outer solar system. This democratization of observation, making raw telescope data available in real time, continues the pattern established throughout the 3I Atlas encounter. The public will not need to wait for official announcements or peer-reviewed publications to see what the telescopes show. They can watch and draw their own conclusions. What conclusions might be drawn? If the December observations confirm the natural comet hypothesis, showing massive debris clouds consistent with the measured acceleration, showing thermal velocity jets, showing composition consistent with exotic but natural interstellar material, the mystery diminishes. 3I Atlas joins the catalogue of unusual comets, remarkable for its interstellar origin, but ultimately explicable through known physics. If the December observations deepen the mystery, showing less debris than expected, showing jet velocities inconsistent with thermal processes, showing compositional anomalies that resist natural explanation, the questions intensify. The trajectory toward Jupiter's Hill radius takes on greater significance. The March encounter becomes even more critical as a test of competing hypotheses. Either outcome advances science. Either outcome tells us something we did not know before. The value of observation lies not in confirming preconceptions, but in revealing reality, whatever that reality turns out to be. There is something profound about watching an object from another star system pass through our cosmic neighbourhood. For billions of years, 3I Atlas travelled through the galaxy, experiencing conditions we can barely imagine. cold beyond anything in our solar system. Darkness interrupted only by the faint glow of distant stars, radiation from cosmic sources bombarding its surface over geological timescales. Whatever this object is, natural or artificial, it carries with it a record of that journey. Its composition reflects its origin. Its surface bears the marks of its travels. Its trajectory through our solar system writes a story in the language of orbital mechanics, a story we are only beginning to read. December 19th gives us our clearest view of this ancient traveller. The data collected during that window and the weeks surrounding it will shape our understanding for decades to come. Future scientists will return to these observations as they puzzle over the nature of interstellar visitors. Future historians may look back at this moment as the time when humanity first grappled seriously with questions about what else might be out there. The telescopes are preparing. The observation schedules are being finalised. Around the world, professional astronomers and amateur enthusiasts alike are calibrating their instruments, checking their predictions, counting down to the date that will give us our best opportunity to understand 3I Atlas before it slips away toward Jupiter and beyond. 269 million kilometres, still impossibly far, but closer than we will ever be again. The December window opens. What we see through it may change everything. The multiplication of improbabilities. Let us talk about probability, not the vague intuition of likely and unlikely that guides everyday decisions, but the precise mathematical framework that underlies all scientific reasoning. When we say something is improbable, we mean we can assign a number to it, a percentage or a ratio that quantifies exactly how surprising it should be. And when we encounter multiple improbabilities clustered in the same phenomenon, mathematics gives us a tool to combine them. We multiply. If event A has a probability of 1 in 100, and event B has a probability of 1 in 100, and both events occur independently in the same system, the combined probability is 1 in 10,000. Each additional improbability multiplies into the total, driving the combined odds into territory where coincidence strains credulity. Professor Loeb has catalogued the anomalies of 3I Atlas with exactly this mathematical rigour. Each anomaly comes with an estimated probability, a measure of how likely it would be for a random interstellar object to display that particular property, and when we multiply these probabilities together, assuming the anomalies are independent, we arrive at numbers that should give any scientist pause. The trajectory aligned within 5 degrees of the ecliptic plane, probability roughly 1 in 500. Most interstellar objects should arrive from random directions, their paths bearing no particular relationship to the disk of planets orbiting our Sun. That 3I Atlas approaches along the ecliptic counter to the motion of the planets, but precisely in their orbital plane, is unusual. The arrival time fine-tuned for close approaches to Mars, Venus and Jupiter, while passing behind the Sun at perihelion, invisible to Earth-based observers at the moment of peak activity. Professor Loeb estimates this probability at roughly 1 in 20,000. The specific choreography required to achieve these planetary encounters while avoiding Earth observation is not something we would expect from a random trajectory. The approach direction coincident with the famous WOW signal from 1977, within 9 degrees of that controversial radio detection. Probability roughly 1 in 170. This could be pure coincidence. It could also suggest a common origin region for both phenomena. The Hill radius match, arriving at Jupiter's gravitational boundary, with precision measured in tens of thousands of kilometres, over a distance of 53 million. Probability roughly 1 in 26,000 based on the geometry involved. The non-gravitational acceleration during perihelion produced exactly the course correction needed to achieve this match. The mass excess, a nucleus roughly 1,000,000 times more massive than Oumuamua and 1,000 times more massive than Borisov, while travelling faster than either. The interstellar medium does not contain enough material to deliver objects this massive to the inner solar system at the rate implied by detection statistics. Probability estimated at less than 1 in 1,000. The unusual chemical abundances, nickel-to-iron ratios unlike any known comet, carbon dioxide dominance in the coma, water depletion below typical cometary levels. Each of these compositional anomalies has individual probabilities that are difficult to estimate precisely, but collectively they suggest formation conditions dramatically different from anything in our experience. The anti-tail that is not a perspective illusion confirmed by Mars-based observation to be a genuine forward-facing emission. The jets that maintain collimation despite rotation, the brightness evolution steeper than standard cometary models predict. Multiply these together, take each probability and feed it into the product. What emerges is a number so small that writing it requires scientific notation, a combined probability that ventures into the realm of 1 in billions or beyond. Now, there are important caveats to this calculation. The anomalies may not be independent, an unusual formation. Environment might simultaneously explain the chemical abundances, the mass, and some of the trajectory properties. Correlations between the factors would reduce the combined improbability. The estimates for individual probabilities are uncertain, based on limited data and potentially flawed assumptions. The true odds might be higher or lower than calculated. Additionally, there is the question of observational selection. We notice 3i Atlas precisely because it is unusual. Ordinary interstellar objects might pass through our solar system all the time without attracting attention. We are looking at a filtered sample, a population selected for unusualness. This naturally inflates the apparent improbability of what we observe. These caveats are legitimate, they deserve serious consideration, and yet they do not fully dissolve the mystery. Even if we adjust the probability estimates generously, even if we assume correlations reduce the combined odds by orders of magnitude, even if we acknowledge observational bias, we are still left with an object displaying a constellation of properties that no known comet has ever exhibited. Something about 3i Atlas is genuinely unusual, not just statistically rare but qualitatively different from what we expect. The question becomes how we interpret this unusualness. One interpretation is that the universe is vast and we should expect outliers. Given enough interstellar objects passing through enough solar systems over cosmic timescales, even extremely improbable combinations will occasionally occur. 3i Atlas might simply be the winning lottery ticket, the 1 in a billion coincidence that mathematics guarantees will happen given enough chances. This interpretation is scientifically conservative. It assumes nothing beyond known physics operating in unusual ways. It requires no extraordinary explanations, only acceptance that extraordinarily unlikely events sometimes happen. Another interpretation is that the accumulation of improbabilities is itself evidence that chance alone is an inadequate explanation. When we encounter a system displaying multiple independent improbabilities, each pushing the odds into extreme territory, Bayesian reasoning suggests we should consider alternative hypotheses that might render the observations less surprising. What alternative hypothesis would make the anomalies of 3i Atlas more probable? The answer that dare not speak its name in polite astronomical company is that the object might not be natural. A technological artifact designed for a purpose would display precisely the properties that make 3i Atlas unusual. A spacecraft entering our solar system would align with the ecliptic for reconnaissance purposes. It would time its passage to approach planets of interest while avoiding detailed observation. It would target gravitationally significant locations like the Hill sphere boundary. It would maintain propulsive capability, allowing trajectory adjustments. Every anomaly that seems improbable for a natural comet becomes less surprising under the hypothesis of design. This does not mean the hypothesis is correct. The burden of proof for extraordinary claims is appropriately high. We should not leap to technological explanations when natural alternatives remain possible. But we should also not refuse to consider technological explanations when natural alternatives require us to accept combined improbabilities that strain credulity. Professor Loeb has proposed what he calls the Loeb scale, a framework for quantifying the likelihood that an object is technological in origin. A score of 0 means definitely natural. A score of 10 means definitely technological. Based on the current data, Loeb assigns 3i Atlas a score of 6, indicating more likely than not to be artificial but far from certain. Other scientists dispute this assessment. They point to the many examples of unusual comets that turned out to have natural explanations. They emphasize the long history of extraordinary claims failing to survive careful scrutiny. They advocate for patience, waiting for more data before entertaining hypotheses that would overturn our understanding of our place in the cosmos. Both perspectives have merit. Science progresses by entertaining new ideas while demanding rigorous evidence. The tension between openness and skepticism is productive, driving us to look more carefully, measure more precisely, consider more alternatives. 3i Atlas has brought this tension into sharp focus. The data accumulated since July contains genuinely puzzling features that resist easy explanation. The probability calculation suggests something unusual is happening. The alternative hypotheses range from exotic natural phenomena to directed technological activity. What will resolve this tension is more data. The December observations, the March encounter with Jupiter, the continued refinement of trajectory predictions. Each new measurement constrains the possibilities, ruling out some hypotheses and strengthening others. In the meantime, we sit with the uncertainty. We acknowledge that something unusual is passing through our solar system. We recognise that the improbabilities have accumulated to a point where simply asserting natural comet and moving on feels inadequate. We accept that extraordinary claims require extraordinary evidence, while also accepting that extraordinary evidence may be exactly what we are accumulating. The multiplication of improbabilities has produced a number. That number demands explanation. What that explanation ultimately is, natural or technological or something we have not yet conceived, remains to be determined. The mathematics does not lie. Something improbable is happening. The only question is what? The threshold. March 16th, 2026. On that date, 3i Atlas will reach the gravitational boundary of Jupiter's domain, passing, at a distance that matches the Hill radius with precision that has become the central mystery of this entire encounter. Whatever happens at that threshold will either resolve our questions or deepen them beyond recovery. The Hill sphere is not a physical barrier. You cannot see it, touch it, or detect it with instruments. It is a mathematical construct, the invisible line where Jupiter's gravity equals the Sun's gravitational tide. Inside this sphere, Jupiter dominates. Objects can be captured, can orbit, can settle into stable configurations around the gas giant and its moons. Outside, the Sun pulls harder, and objects simply pass through. The Lagrange points L1 and L2 sit precisely at this boundary. These are positions of gravitational equilibrium, where an object can remain stationary relative to Jupiter with minimal energy expenditure. We exploit these points in our own space missions. The James Webb Space Telescope sits at Earth's L2 point. A technological civilization with knowledge of orbital mechanics would understand the strategic value of these locations. If 3i Atlas were to release something as it passes the Hill radius, if smaller objects were to detach and slow down enough to be captured by Jupiter's gravity, the Lagrange points would be the natural destinations. Minimal fuel required. Stable positions maintained indefinitely. Perfect vantage points for observing the Jovian system, or anything else of interest in the outer solar system. This is speculation. We have no evidence that 3i Atlas will release anything. We have only the improbable precision of its trajectory, the course correction during perihelion that produced exactly the approach distance needed, the statistical anomaly of arriving at the one gravitational boundary that matters. The Juno spacecraft will be watching. From its orbit around Jupiter, Juno's instruments can scan the region where 3i Atlas will pass. Its cameras can image the interstellar visitor from a perspective unavailable from Earth. Its particle detectors can sense material in the extended debris cloud. Its magnetometer can detect perturbations in the local magnetic environment. If something happens at the Hill radius, something unexpected, something that does not fit the natural comet narrative, Juno may be positioned to observe it. The spacecraft was not redirected to intercept 3i Atlas directly, but it will nonetheless be the closest human-made observer during the critical encounter. ESA's JUICE spacecraft, currently en route to Jupiter, will observe from a greater distance. Its instruments are designed for planetary science, but like Juno, they can be pointed at unexpected targets. The data from JUICE will complement what Juno provides, offering different wavelengths and different sensitivities. From Earth, the viewing geometry in March will be challenging. 3i Atlas will be distant, faint, moving against a star field that complicates detection, but major telescopes will try. The Hubble might capture images if observation time is allocated. Ground-based facilities will push their limits. What outcomes are possible? In the most conservative scenario, 3i Atlas simply passes through the Jupiter system without incident. It crosses the Hill radius, continues outward, and eventually fades from detectability as it recedes into interstellar space. The The trajectory coincidence is recorded as a remarkable curiosity, perhaps the subject of future statistical studies about the distribution of interstellar object paths. The mystery remains unresolved but static. In a more interesting scenario, something changes at the Hill radius. Perhaps the object fragments, releasing smaller pieces that follow divergent trajectories. Perhaps there is an outburst of activity, a sudden brightening or jet formation coinciding with the boundary crossing. Perhaps the tracking data shows unexpected accelerations that were not present during the earlier part of the trajectory. Any of these observations would demand explanation. Fragmentation might indicate structural weakness triggered by changing gravitational stresses. Outburst activity might indicate volatile reservoirs exposed by some internal process. Unexpected accelerations would require accounting for forces beyond normal physics. In the most provocative scenario, something is detected that cannot be explained naturally, objects separating from 3I Atlas and decelerating into Jupiter orbit, electromagnetic emissions of technological character, behaviour that matches no natural process we understand. This scenario seems unlikely. If 3I Atlas were a technological probe, its builders would presumably prefer stealth over advertisement. Why reveal yourself at the moment of closest scrutiny? But we cannot rule it out entirely. The accumulation of anomalies suggests that our expectations may not apply. Whatever 3I Atlas is, it has already surprised us repeatedly. The waiting is difficult. 4 months separate us from the Jupiter encounter. 4 months of continued observation, of refining trajectory predictions, of debating interpretations. 4 months during which 3I Atlas will grow fainter and more difficult to study as it recedes from the inner solar system. And then March arrives. And then we know, or perhaps we do not know. Perhaps the encounter is ambiguous, providing data that can be interpreted multiple ways. Perhaps the mystery persists, neither confirmed nor resolved, leaving us to wonder indefinitely about what passed through our cosmic neighbourhood in 2025 and 2026. Science is comfortable with uncertainty. The history of discovery is filled with questions that remained open for decades or centuries before resolution. The nature of 3I Atlas may simply join this catalogue, a puzzle for future generations equipped with better instruments and more complete theoretical frameworks. But there is something different about this question. It touches on our fundamental understanding of our place in the cosmos. Are we alone? Have others sent emissaries, probes, observers to study what exists around other stars? The possibility that we're being watched, that our solar system has visitors from elsewhere, carries weight beyond normal scientific curiosity. The threshold approaches. Jupiter waits at the edge of its domain, the largest planet in our system, the gravitational anchor of the outer solar system. 3I Atlas continues its trajectory, indifferent to our questions, carrying whatever secrets it holds toward that distant encounter. We will be watching. From Earth and from space, with instruments ranging from amateur telescopes to flagship observatories, we will record what happens. The data will be preserved, the analysis will be published. Future historians will have access to everything we observe. What they make of it will depend on what we see. The threshold approaches, and we approach it with wonder. As the quiet hours deepen and the stars wheel overhead in their ancient patterns, let us take a moment to reflect on what we have explored together tonight. An object from another star, travelling for billions of years through the cold spaces between suns, has passed through our solar system. It came from a direction near the famous WOW signal. It aligned its trajectory with the plane of our planets. It timed its arrival to pass close to Mars and Venus and Jupiter, while hiding from our view at its most active moment. And now it approaches the gravitational threshold of the largest planet, arriving at the Hill radius with precision that mathematics struggles to attribute to chance. We do not know what 3I Atlas is. The evidence accumulated since July contains genuine puzzles, anomalies that challenge our expectations, the jets that refuse to blur, the chemical fingerprint that matches no known population, the trajectory correction during perihelion that produced exactly the course needed for the Hill radius match. These mysteries may have natural explanations. The universe is vast and strange, and we should expect outliers. But they may also point towards something more profound, toward the possibility that we are not alone in this galaxy, that others have sent technology to explore what lies around distant stars. Either answer changes how we see ourselves. If 3i Atlas is natural, we learn that interstellar space contains objects more diverse and surprising than we imagined. If it is technological, we learn that we share this cosmos with intelligence capable of interstellar travel. Thank you for joining me on this journey tonight. Your curiosity, your willingness to engage with difficult questions, your presence in this community of wonder seekers means more than you know. If you found value in what we explored, consider sharing it with someone else who might appreciate the mystery. And if you have not already, like and subscribe helps bring these explorations to more people. The disclaimer, as always. What we have discussed tonight represents current understanding mixed with speculation. The scientific process is ongoing. Conclusions may change as new data arrives. Approach extraordinary claims with appropriate skepticism while remaining open to extraordinary possibilities. The stars continue their ancient dance above us. Somewhere out there, 3i Atlas continues its journey toward Jupiter and beyond. We are small, a single species on a single planet in an ordinary solar system, but we are curious, we ask questions, we look up, and sometimes something looks back. Good night.